Hello everyone. Today we are going to start chapter 3 and this chapter will be specifically on quantum information theory and many different properties of quantum information theory. All right. So first, what do I mean by information? Information is represented by distinguishable states of a physical system. That means, okay, let me write it down. Information is something, is represented by distinguishable states of a physical system. All right, so if you can physically distinguish between the two states, then they carry two different information. All right, so that's the definition of representation of information. But classically there is no problem. If you're given a system, you can do measurements on it and it doesn't change the system, and then you can read it and then process it as however you want. But quantum mechanically it is a bit different, as you have already learned that when you have a quantum superposition and you perform a measurement, it collapses to one of the states, so it changes the state. So this is a bit different in quantum information. And if you remember correctly, if you ask classically that if you have n bits in a classical computer, then you can represent at most 2 to the power n pieces of information. Or okay, let me write it in a shorter language. You can encode 2 to the power n messages. All right. So what happens in a quantum system? If you remember correctly, let's say that you have a quantum state psi, which belongs to a d-dimensional vector space. All right. So although there are infinite possible combinations of psi, if you remember correctly, that to distinguish two or many states by a quantum measurement, then they have to be mutually orthogonal. Orthogonal. Yes. So what I mean by that, so if I write psi in a basis like this, let's say let's not give a precise number, some possible combination of plus and 0, then you cannot say that by a measurement the probability of getting plus is a square and probability of getting 0 is modulus of b square, and you cannot distinguish them via a physical measurement because they are not orthogonal. Okay, but if it were plus and a minus, then you could have done that. All right, so this is the idea that if you want to distinguish different possible states, they have to be orthogonal to each other. That's the main idea of this statement. Okay, so they are different pieces of information only if they are orthogonal, and as psi belongs to a d-dimensional vector space, there are only at most d mutually orthogonal vectors. So you can at most encode d different messages. All right, so although the psi can be in like infinite possible of superposition, infinitely possible superposition states, but you can only encode d different messages, because when a piece of information is given by a measurement, and whenever you do a measurement, you cannot have more than d possible outcomes because they have to be mutually orthogonal. All right, so this is the idea of quantum information. So this is a very important statement. All right, if you are in a d-dimensional vector space, you can at most encode d different messages or pieces of information. All right, and one more thing to notice is that if you are given as pure state psi, if you're given a pure state psi, then what we say is that this is a piece of quantum information. Although I don't know precisely what the state is or what are the possible what precisely the state is, yes, but this is a piece of information because this is the stuff that is used in quantum computing and in communication via quantum channel. Okay, so this is a bit different from a classical information, because whenever I say a classical information, that you precisely know what it is, you can do measurements and you can see what the string is, but whenever I talk about quantum information, this is just a pure state. All right, so you precisely don't know, you have some stuff which you can use, and this is a bit more general than the classical information. But what happens is that measurements by measurements I mean quantum measurements provides a link back to classical information. Okay, because when you collapse, when you perform a measurement, it collapses and you precisely get a known quantum state. All right, and that is where you connect it with classical information. So quantum information is a bit more general. It's an arbitrary quantum state, but you can perform measurements on it, and then you can connect it with the classical information. And whenever you have quantum information, that means a quantum state, you can perform operations on it, and you can use it for communication via quantum channels. All right, so classical information is a special case of quantum information where the quantum information is taken from an orthogonal set. All right, so if this is not clear to you, I would strongly recommend that you start reading the notes, or you can discuss it in the live session. All right, and one more thing I want to introduce is there will be some operations that we can do on quantum information for quantum information processing. So these processes, I'll list them now. The first one is ancilla. So what is an ancilla? So let's say, okay, before introducing that, I want to say that I have a unknown quantum state psi. Okay, I have some unknown quantum state psi, and I can do some operations on it to do quantum information processing. All right, so what can I do? I can add an ancilla to it. What is an ancilla? Ancilla is a known quantum state. So you know this quantum piece of quantum information, known quantum state. Okay. All right, so and what you do is that you join them, you make a bigger space. All right, so by joining I mean there is a tensor product here in the middle, but I guess you understand it by now. So what's the benefit here? The benefit here is that, let's say that psi belonged to some vector space which was d-dimensional, okay, and A belonged to a vector space which was d prime dimensional. Now when you merge them together and you add an ancilla, then you are working with a d into d prime dimensional vector space. Okay, and as we say that okay, let me finish it. As we said before, that the number of dimensions in the vector space you're working on gives you the number of independent messages that you can encode. And if you're enlarging the dimension of your space, then you can encode more messages in that system. All right, and this will work for our advantage. Okay, and the second operation that we can do is a unitary transformation. Okay, I explained it to you already before, that why do I need a unitary transformation? Because I want to preserve angles between the vectors, and I want to preserve the norm of the vectors. And if you remember from the last few videos, that we introduced some quantum gates, and those were also unitary transformations. So if you want to do some quantum information processing, you for example, you want to add two numbers, right, and you use some gates, you call them adder in classical computers, right? So you can similarly, you can use some quantum gates here in quantum information processing, and those will be unitary transformations. All right, so if you're given some psi, you can perform some unitary transformation and go to u psi, where u dagger is equal to u inverse, because this is a unitary transformation. All right, and last is a measurement. All right, so if you're in some state psi, and you can obviously perform a measurement, possibly only in a part of it, not a complete measurement. It can be an incomplete measurement as well, and it will collapse to a new one. Let's call this psi new. All right, and you can perform a measurement. This is a post measurement state. Post measurement state, and all the probabilities, if it is an incomplete projective measurement, then this new state, the collapse state, all the probabilities will be given by Born rule. All right, so these three are the most general. I mean, any general action can be thought of as a combination of these three operations. They can be in a particular order depending on the problem you are solving. but these are the only 3 operations that is required to perform any any general quantum action. All right. So we will be using these operations when we are building quantum circuits and when we are doing quantum algorithms. All right. So I hope it was clear, and if not, we can discuss about it in the live discussions. But I would strongly recommend that you start reading the notes, and which is page number 23 in the notes. All right, chapter 3. So thank you so much. I hope you enjoyed it.